talk about the bijection for covered maps on orientable surfaces.
Thank you. So I would like first to thank the organizer for giving me the opportunity to talk here in this workshop. I will present a joint work with Guillaume Chapuis from École Polytechnique about covered maps. So I will come to precise definition. Oh, sorry. All right. So I will present a work on covered maps. I will not tell you yet what they are, but for the moment you can think of them as a map plus an additional structure that covers it. So this is the outline of the talk. I will recall the definitions about maps, tree-rooted maps, and covered maps. So tree-rooted maps are just a map plus a spanning tree. And covered maps are a bit more general, but in the planar case, they are the same. So in the planar case, the covered maps are just a map plus a spanning tree, distinguished. And the main result of the talk is this bijection between covered maps and pairs made of a tree and a unicellular bipartite map. In the planar case, this is a bijection between tree-rooted maps and pairs of trees. There is a couple of references here. So Merlin was probably the first to study tree-rooted maps, and he found a very nice enumerative formula that suggested that such a bijection should exist. And this led Corey, Duluc, and Vienno to find a bijection explaining this result. But this bijection is indirect, so it goes to parenthesis shuffle, and then it makes a recursive bijection to find a pair of trees. And a more direct way of doing was given here. And these are other people that worked on tree-rooted maps on higher genus surfaces. But on higher genus surfaces, what I will talk about, covered maps are a bit different. Okay, so once I've given this bijection, I will give some of its properties, and I will say how it behaves with respect to duality. And then I will point out a relation with the classical bijection of Schaeffer, the one that you have seen this morning, and its extension by Boutier, Di Francesco, and Gitter. So, in fact, this bijection generalizes this one, and and I will explain now. Okay, so first definitions. So maps, we have seen the definition this morning. It's a planar graph, a connected planar graph embedded in the sphere, and we consider this object up to deformation. So these two maps are the same, but it is different from this one, though it is coming from the same planar graph. And a map is rooted. We will work with rooted object by distinguishing a half edge at the root. This one, for instance. In this talk, I will find it convenient to indicate the root otherwise, just by drawing a little arrow like that in the corner preceding the root. It's convenient for a reason that will appear later, but it's obviously equivalent. Sorry?
Preceding means what?
So preceding means it is preceding the half edge.
Yeah, but which of the three does it precede?
So in this case, it precedes in, so you have to say in counterclockwise order or clockwise order. So it precedes in counterclockwise order. But it doesn't matter. You might as well think that you write the root this way, and this is your root, and you don't have really to think about which half edge it is pointing at. Okay, it's just convenient. It is the usual way of rooting trees, but also here it will be convenient for me to use this root like that, but for reason that will appear later. Okay, so now tree-rooted maps, as I said, it's a map plus a distinguished spanning tree. So here you have an example. the spanning tree is in red. And there is a nice property of this object by duality. So if you have a planar map, you can define its dual. It's defined by putting a vertex in each face and an edge across each edge, like this. This is a dual of my map. So what I'm not saying, I'm maybe skipping some standard vocabulary because it was used this morning, but a face are the connected component of the complementary of the graph. And I've put a vertex in its face, these white vertices, and I have connected them through all edges. This is the dual map, and if you look at a tree-rooted map now, so you have this spanning tree in red, and in the dual map you take all the other edges. So you take all the edges that go through the blue ones. So these are the cyclines edges. These define a tree of the dual map. So there is a bijection between the spanning trees of the map and the spanning tree of its dual. All right. Now, this is the numerative result I was talking about a bit earlier. So, a result by Moline saying that the number of true-rooted maps with n edge is given as the product of two Catalan numbers, Catalan n times Catalan n plus 1, where Catalan are these numbers. And for n equals 2, I have drawn all the true-rooted maps, and you can check that there are 10 of them, which makes 2 times 5. So we are happy with this formula. And I should mention that the proof uses a correspondence of true-rooted map with shuffles of two trees, or maybe I should write shuffles of two parenthesis systems. But the results here suggest a pairs of trees, a pair of trees. And this was what led Corey-Duluc and Vieno to look for a bijection. And this one is a bit more direct, working on maps. Okay, now the definition will be a bit more subtle for. I'm going to cover maps, but so I have to explain first what are the maps in higher genus. So on higher genus, it is what you expect it to be. So a map will be a graph plus a cellular embedding in an oriented in this surface considered up to homeomorphism. So these two maps are the same. But you have to be careful about this word, cellular. It means that the faces, the connected component of the complementary, have to be homeomorphic to the disk. So this is not a map in genus 1. Okay. Now I have to recall one more thing about these maps and higher genus. It is another way of looking at them, saying that a map is just a graph plus a rotation system. A rotation system means I'm choosing a cyclic order of the edges around each vertex. So why are these? So here I've put an equivalent sign. It means that there is a one-to-one correspondence between these two objects. They are the same objects, and can at least make precise how you go from a map to a rotation system. But it is very clear. You look at the counterclockwise order of the edges on the surface, and this gives a rotation system. So why is that one-to-one? So what I'm saying is that if I am given a rotation system, there is a unique surface and a unique embedding on this surface, giving a map, a topological map. And the reverse way would be to look at fat graphs. So I have this rotation system, so I can expand my edge a little bit. I will obtain something that looks like that. And now I want to, I know that this it is locally what is around my graph on my surface. And I also know that the face have to be homeomorphic to the disk. So here I have no choice but to look at this. I look at the border of the faces, and on each of these borders, I will have to glue a disk if I want this face to be cellular. So there is no choice, and I will recover.
How do you get the fat graph from the three things?
Here, so you have this cyclic order. You decide this cyclic order represents a counterclockwise order, and you just you have your edges, and you just say, well, expand them a little, and this is a fat graph.
Oh, but they are connected. You have the three.
Yeah. It's I've only represented the rotation system, but it is a graph plus a rotation system.
Oh, the graph. Okay. Yeah.
Yes. Okay. So I will use a bit this definition. That's why I'm insisting on this equivalence. So now a map is unicellular if it has a single face. So here you have a unicellular map on the torus, and just remark that in the planar case, these unicellular maps are the trees. Okay, now comes the definition. A covered map is a map with a distinguished unicellular spanning subgraph. So I have my map, and I have a spanning subgraph, which means I have a set of edges that connect all my vertices, and I ask it to be unicellular. So if I forget about the blue edges, I have a unicellular map. The tricky thing about this definition is that, okay, the easy thing about this definition is that in the planar case, these are just tree rooted maps. So I'm just choosing a tree on my map, a spanning tree on my map. But if I'm looking at genus G surfaces, the submap can have genus 0, 1, 2 to G. In fact, I'm looking at this submap as a map in itself. So its rotational system define a genus, and you look as such if it is unicellular. I mean that, for instance, so this is a covered map, but this is also a covered map, and here this thing is unicellular in its own world. I mean, in its world of this is a planar object, and as a planar object, it is unicellular.
So when it's unicellular, where?
It is unicellular if you consider this as a rotation. So you consider this object, the submap, as a map in itself.
Oh, okay. So
And then
surface.
yeah. So this is the tricky part of the definition, that the unicellular submap I'm considering can be of any genus between 0 and G.
Is it true that you can talk about the genus remaining in the single cell of the
Yes,
unicellular?
sure.
And this plus the
This is
number of loops in the pseudo tree is the original genus?
That's right. So I'm coming to it. So now take covered maps. I can do the kind of the dual construction I was doing in the planar case. So this red thing here is also a covered map, and it is also a covered map. If you look here, for instance, the red spanning subgraph is of genus 1, while the green one has genus 0, and 0 plus 1 sum to 1. And more precisely, what I want to say is that I have that covered maps of genus G with n edge can be seen in bijection with what I call shuffles of two unicellular maps, and the genuses divide is shared and the edges are shared. Right. So just take two unicellular maps and try to glue them together. It's easier to think of it in the plane, but it also work on higher genus surfaces. So in the plane, you just take two trees, and you say they are like this, and you have to say exactly how they shuffle. Okay, so that's all for the definition, and now we are coming to the results. So it will be a bijection between covered maps and pairs made of a tree and a bipartite unicellular map. And if you were not too much convinced about this higher genus thing, you can still think of it in the plane, and it's already a bijection.
That can be any genus now.
Yes, yes, yes.
And then does it translate into something on the other side?
Sorry. So so here is the answer to the question. The bijection, more precisely, is between covered maps with n edges and genus G, and pairs made of a tree with n edges and unicellular bipartite map of n+1 edges and genus G. So all the genus comes here, and this is just a tree. And the philosophy of this bijection is that these covered maps are a tree that is folded to itself in order to construct a map. And this is telling you how to fold this tree into the map. So this is the philosophy of this thing. And in fact, the bijection is in two steps. So first, I will associate an orientation to my covered map. And then I will do a second step in order to split my oriented map into two objects. And for those of you that were here on the workshop 2 weeks ago, this will remind you of what I was doing 2 weeks ago. Okay, so first step, the orientation. So I'm starting from a covered map. So I have a map and a spanning submap. And this spanning submap is unicellular. It means I can make its tour. And doing its tour, I will visit all the edges of the map. So what I call making its tour is following the border of the edges of the submap until I return to the root. And associate to this submap and orientation. So the rule is that I orient internal edges. So the edges in the submap I orient. This has no meaning anymore. Sorry. Okay. So I orient them. Okay. There is a mistake in my. I have made the copy and paste from my previous talk, and there is a bit a small subtlety here. So let's say at this second line, this is correct. So I orient external edges, so these are the blue edges, in such a way that the ingoing half edges are encountered first. So let's take an external edge, this one. When I make the tour of the submap, I encounter first the ingoing half edge and then the outgoing half edge. Okay, and let's say that for internal edges, I ask the opposite. Okay, I will not write it. I just ask the opposite. So I want that for an internal edge like this one, I encountered first the outgoing edge, the outgoing half edge, and then the ingoing.
It sounds circular. You first somehow construct your tour.
Yeah. So you are orienting the submap in the way that you are visiting it. That's right.
So this is not construction of the tour, what you are describing.
No, no, no. The construction of the tour, you don't have any orientation. You have your route. You start and you want to follow the edges in counterclockwise direction, starting from the root. That's all. Okay.
If it is genus 1, there is no problem. You somehow.
Yeah. There is one face, and this is the only thing important. Okay. So first remark: this mapping from unicellular map to orientation is injective, and the reason is coming really from this property that for internal edges you first see the outgoing edge, and for external one you first see the ingoing half edge. So I can try to reconstruct my submap by just starting a tour, and whenever I encounter an edge for the first time, I will be able to decide if it's internal or external. So here, if I start, I first encounter this half edge. It is external, and I know that it has to be in my submap. So I colored it in red, and I follow its border, and I fall on this ingoing half edge. So I know it is external. I color it in blue, and I cross it, and so on. So at each step, I will be able to decide, and when I have finished my tour, I will have my submap colored the right way. Okay, so this is injective. Now comes the second step, and the second step is a local operation that you do on each vertex. So I consider a typical vertex of my map. It has a certain number of ingoing half edge and certain number of outgoing half edge, but it has at least one ingoing. So maybe I should say why. Well, because the submap, you have oriented it. So when you are making the tour of your submap, you are visiting every vertices. But when you arrive to it, you arrive by a red edge, and so this red edge is pointing at it. So, okay, let's consider this. This. Sorry.
With the possible exception of the root?
Yes, all right. So exactly. So with the possible exception of the root, but I will now consider this as an ingoing half edge. So this is why it was interesting for me to denote the roots in this way. Well, it's just for simplicity, I mean. So I will draw this this operation here. So this is just the general situation, and I blow the vertex. So it has a certain number of ingoing half edge, and I will create as many vertices as half edge. So one vertices per half edge, and the outgoing half edge. One vertices for ingoing half edge, and the outgoing half edge, I distribute them in the way that is indicated in this picture. That is, an outgoing half edge is associated to the ingoing half edge following it around the vertex. So you obtain something like this. So okay, so this is the local operation that you will apply to each vertex. So let's try an example. You have this oriented map, and you apply this local operation. To be to define things properly, I should also mention that if you have just one ingoing alpha edge, then you draw this cell I have not talked too much about, but this blue cell I will indicate it on its right side. Okay, so here is what I obtained on my example, and a very strong property of this the map I obtained is that it is a tree. So it is a tree with all the edges of the original map, with n edges, and okay, so this is a striking property. And now what I want to do is so yeah, I have this tree, and I want also to build a second structure that will tell me about these blue cells, because I want to remember these blue cells in order that this mapping to be bijection. So what I will do is to draw the dual vertices. So I draw a vertex in each face, and I connect this vertex to each of the blue cells I can reach without crossing the tree. This is what I obtain, and I call this structure the mobile because of the bijection of Boutier, Di Francesco, and Guiter. And it turns out that this mobile is a bipartite unicellular map of genus G with n+1 edges. Okay, so the reason for that is that when you have this tree, in fact you are kind of you are drawing a map on the complement of this tree, so it will be in fact be unicellular. This is more or less the reason for that. Okay. So now what I say is that I can split this structure into two parts. On one side I've put the tree, and on the other side I put the mobile. And the claim is that this mapping is a bijection between covered maps and pairs made of a tree and a mobile. So if you started from a covered map with n edges and genus G, you will have a tree of n edges and a unicellular map of n+1 edges and genus G. So I said yes, the edges that I have are so the edges of this tree are just the edges of the map, so there are n of them. And why are there n+1 edges? Well, in this bipartite map, each blue corner corresponds to an ingoing alpha edge of the original map. And there are n ingoing alpha edge plus the root, so n+1. Okay, so this is the main result. Just a word about the reverse bijection so that you understand how it works. So the basic thing is that when I've put these two objects apart, I've lost no information at all. In fact, what I want to do if I want to do the reverse operation is to glue the tree around the face of the mobile. And I will glue the left corners, the right corners, so the corners on the right of each. So if I have a vertex here in my tree like this, this is the right corner, and this is the one I want to glue to a blue cell. I will glue them to the blue corner of the mobile. Okay, so this is what was indeed happening in my construction when I have the two things together. Okay, so I have no choice to do that. I mean, I will I will start putting my tree on this face, and I want to glue each vertex of my tree one by one on each of the blue corner of the mobile. So it starts like this. I just glue them one by one, and the order is given if I don't want to have any crossings. So there is no choice. So I glued my tree on the mobile. Then I can forget about my mobile. I contract the blue cells, and then I have an oriented map, and from this I recover the spanning submap. Okay. So I hope you are convinced that these things are well defined. So now some special case when you are in the genus 0 and the planar case. This gives a bijection between tree-rooted maps and pairs made of a tree and another tree of size n+1. So this explains the formula of Merlin. And this bijection is isomorphic to the one of Corey-Duluc and Viennot, in a sense that I will not explain. Well, see, yes, I will explain. So what I mean is that if I start with from my map, I can associate to it a parenthesis shuffle. And if I apply this bijection, I will obtain two objects. And if I apply the bijection of Corey-Duluc and Viennot, I obtain two objects. And the composition is acting independently on each component. So if I compose like this, like this, like this, it can be described as you have a pair of objects going to a pair of objects, and these are all bijection. And here it's the Corey-Duluc and Viennot bijection. And here is the bijection I just described, and you obtain not the same thing, yes, if you want, or you can say more it says that this composition, you can find two independent maps acting on the two components, and they act independently. Yes?
This is counting what in random matrix we can call the logarithmic model, the one in which you have all possible degrees, in a sense, in generating function degree k as a weight g to the k, and they are not constrained in any other way.
Yes, that's right. So we are dealing with general maps, and if you want to count vertices by putting weights on, yeah, so you just say that.
You can do only the multiplicative one.
Yes. I'm counting the edges, not the degree. I'm not prescribing the degree. I don't recall the degree sequence. I just recall the number of edges. So it's multiplicative in the sense that you can say the number of edges is the sum of the number of half edges.
So you cannot
divided by
constrain
2.
the degree.
No, I do not. It's really all maps, all trees.
There is an abstraction for doing this, for doing the fixed degree.
What do you mean?
The question, I guess, is whether you can recover the degree from your bijection.
Oh no, you cannot. I mean, you can specialize this bijection. In certain very special cases, you can say what you obtain at the end. I will say a few words about that at the end of my talk. But in the general case, I cannot say. It's a very specific example where I can really say what is on one side and what is on the other side. Okay, so another enumerative result about about genus 1 case. So in the torus case, duality implies that half of the covered maps are tree-rooted maps, mean that the submap is either of genus 0 or of genus 1, and if it's of genus 1, the other is of genus 0. So you have this property that the number of tree-rooted maps is half the number of covered maps, and the number of covered maps you can determine because you know what is the number of trees and what is the number of bipartite unicellular maps, and you recover like that an unexplained formula of Levin and Walsh. Okay, so this was for general bijection. Now I want to say a few words about duality of this bijection. So as I said, there is these covered maps are dual object. If I take the dual of a covered map, is a covered map. And what is happening is that the bijection behaves very well with respect to this duality. First, the orientation associated to the dual map is the dual of the orientation associated to the map. And when I say that, I mean that if my primal edge is oriented this way, the dual edge will be oriented this way, if I'm not mistaken. Right. Okay. And okay, we stick to that. And the second property is that the unfolding step can in fact be performed simultaneously on the covered maps and its dual and give the same mobile.
Is it true that if you, on the direct one, you say that you attach the clockwise, on the dual you attach the counterclockwise?
That's right. So I have skipped this little details. So here is my map. I have an orientation convention around my vertices. In fact, in the dual world, it will be the dual convention. So, for instance, when I make the tour of my tree, I want to do it counterclockwise. In the dual world, I do it clockwise. And these are simultaneous. When I do the tour of one of the tree, I make the tour of the second one. And when so in this sense, this one is involutive. If I apply it 2 times, I will recover the same. And also here I have indeed chosen the convention for blowing these dual vertices, which is the dual of the convention I used, which means that this drawing will be a bit different, will be reversed. Okay, so this is what I claim. So here is what the bijection on my primal map, and the duality. The dual bijection is isomorphic in the sense I was saying before, meaning that if I apply the same bijection on the dual covered map, I will obtain a mobile B and B star and 3T star that can be obtained by independent maps from the mobile B and the 3 2. Yeah. Alpha is just this. I just keep my mobile. As I said, the mobile do not change. Just the routing is changed. So it exchanges blue and white vertices. And for trees, there is a way of describing this map. But it's the dual tree. And there is a description of this dual tree in terms of exchanging 8 code with Lukasiewicz code that I will not enter, but it's a nice involution on trees. Okay, now I come to the relation with other bijection, other non-bijections, and for that I will consider the 8 code of the tree. So if I have a tree, I can make it 2 and record the 8 of each vertex. So the root is at 8 0. It is always 0, so I do not write it. Then I will. Here I'm at 8 1, 8 1, 8 1, 8 2, 3, 4, 5, 3, and 2. This is the 8 code of my tree. So a sequence of labels is positive integers is the 8 code of a tree if the sequence do not increase by more than 1 at a time, and the labels remain positive, and they cannot increase by more than 1. Now the idea is that I will code the tree by a label sequence on the mobile. So I have to glue. So I have my 2 objects, the tree and my mobile, and I don't know I have to glue my tree on the mobile. So I can as well remember my tree by putting the 8 code on each of the blue vertex of my mobile, which is done what I have done here. And if I'm looking at such an object, I can recover I can draw the tree with a very simple rule that from each blue corner I will draw a line coming from the last corner labeled I-1 appearing before it around the mobile slice. This was the rule that was used this morning in the talk of Jean-François. Okay, so now I will look at a very special case where the labels coincide around each blue vertex of my mobile. So here is an example. In this case, I consider this label to be a label of the vertex, and I apply this rule, and the claim is that when this label coincide around each vertex, the orientation that I obtain is geodesic. It means that the labels correspond to the distance from the root vertex, and the orientation is from I to distance from distance I to I plus 1.
So what do you mean the labels coincide?
I mean that, so remember that here, where am I? Okay, sorry. So remember that here I'm labeling corners and not vertices. So what I call coincide is that all the corner of the vertex have the same label, like this.
This has a meaning in the kind of Brownian description we are giving.
Well, I don't know what you mean by that.
Something like the Brownian escalation.
Yeah, it has this meaning exactly. It has the meaning that you have to be at the same 8 each time you return to a vertex. So okay, and if I want to go really to the tree, I can say what it is, but it's not very important. So in this case, the tree will be the first BFS tree of the map, which happen to be bipartite. This is easily seen to be bipartite because each edge go from a label with odd to even labels. So BFS is a breadth first search algorithm. So if I have let's say that I have my bipartite map. I want to explore it, and I use the breadth first search algorithm, which means that I'm starting from the root. I explore all its neighbor, and then I consider this neighbor in this order. I consider again all its neighbor, and then I repeat this operation again and again until I have explored all my trees, my map. So here I will do this, then I will do this, and then I will do this. And if I orient it, this is the geodesic orientation. But this is just a remark. I mean, it's not nothing very important.
Is it true that this special case of concerning labels is not routing independent? If you change route, it can break stuff.
Sorry, can you repeat the beginning?
The word class is route independent. You choose a route just for technicality, but in a sense you are labeling everything. But here, this special case is a family which is route dependent.
I think it's always route dependent. I don't really see what you
that
mean.
the same graph, if you change the position of the route, is not in a special case anymore.
No. I mean that if you change the route when you will it has no meaning at all. But if you change the route, you will have a different labeling of the vertices, and then you will have a different orientation.
This is a bad feature.
No, it's not a bad feature because I don't change the route. I mean, I want to count. Okay, first I say what I want.
From the very beginning.
Yeah, I have a route from the very beginning, and I want to keep it all the way.
Well, but all the other results were route independent this time. If you change it, everything
They are
goes.
not root independent, I would say, because the root is always there. The root is there. It's about rooted objects from the beginning.
Well, sorry.
Okay. So what I want to say. So it's written here. So I have this. This is the general bijection between covered maps and pairs of objects. So this pair of objects, I can represent it by a labeled mobile, and if the mobile coincides around each vertex, then I fall in a subclass of a smaller bijection between bipartite map plus the first BFS and well-labeled mobile. And this is the bijection of Boutier, DiFrancesco, and Gitter. And if you specialize a bit more by supposing that the wide vertices have degree 2, you fall on this case of Schaeffer that we have seen this morning. Okay, and I have not much to say left, apart from some counting results. It is possible to count well-labeled mobile. So, in fact, so we have specialized our bijection, and we are able to characterize the product, the object that we have obtained. So we are able to count this well-labeled mobile, and in this case, it's possible to recover from that the number of bipartite map with n edges and this and fi faces of degree 2i is given by this very nice formula that was first discovered by Tutt. There is a bijection by Schaeffer explaining this, and it can also be obtained from this mobile construction. And there are other cases where you can apply, you can specialize the covered maps bijection, and you are able to describe the object that you obtain at the end. So if you start from a triangulation with a specific orientation on it, you will be able to count the mobile that you obtain at the end and recover. So you obtain a bijection, which is different from the one of Poulalou and Schaeffer, but which gives the same result of TUT, giving the number of triangulations of size n. And also, it is possible to specialize to a special type of quadrangulations and to obtain from that the number of non-separable maps of size n. So you can specialize this covered maps bijection in at least 3 different ways, but probably more, and obtain like that bijection for specific families of maps. And yeah, that would be all. Thank you.
I have a sort of a question. I understand that your covered maps were initially understood as shuffles, right?
Yes.
Of what was it? J plus H and G
yes,
minus H
yes.
on one side, and also edges
Right.
turned into 2 subsets.
Yes.
So do you understand the relationship between these shuffles and this factored, sort of factorized picture you're showing us? I mean,
Well, I understand it
very
like this.
does it result, for instance, in combinatorial identities, like sums of products?
So there is no.
I'm thinking just about the Catalan.
Okay,
numbers,
so the
right?
Catalan
There's an
case
identity
is
which
quite easy, in fact. If you look at what you obtain from the shuffle description, it is saying that number of true-rooted maps of with n edges. You say that you have a primal tree of size k, a dual tree of size n minus k, and you have to shuffle it. So this will be Catalan k for the choice of the primal tree, Catalan n minus k for the dual tree, and the shuffle. So you have to choose a 2k. To choose a 2k among 2n. And then there is a true van der Monde identity that gives the results. So you would have to write this in, I don't know if I want to do that, especially because I have a chance to fail. But it's not hard. If you write it down, it's very easy, and you really
You get this as
just
product.
this
So
true.
my question, I guess, is you have here generalizations.
Yes,
of
yes.
that identity.
Yes.
And do they relate to something known or?
But already the number of unicellular map is not very nice. So this gives a strong. Maybe in the torus case, toroidal case, it gives something. Yes. But after genus 1, I don't think there is a closed formula for unicellular or bipartite unicellular maps. So.
Could it be related to what we saw this morning with the first one?
Bertrand?
Bernard?
Loop equations.
I don't see the connection,
Shuffles
but
look very much like loop equations.
I would guess that you would like, for instance, for genus 2, you would have a sum of 3 terms, like 3 graphs. That would be my guess.
so I don't know maybe there are, but I would like to know.
Just a curiosity towards also this basic part of the lecture. Could it be that these unicellular subgraphs form a matroid? So for planar graphs, there are trees,
So
and
you
they or acyclic
so you would like to have them as base of a matroid, but then you would have
well, or no, just matroid, because isn't it that the subgraph of a
so you don't
unicellular-
take them spanning. So what
No,
do you?
just all. Well, yeah, you are right, because they must be connected. Right? So maybe maximum unicellular as
Take,
basis of the map.
I can give you an example where you can do something. Take the toroidal maps. You can take as the base of matroids the unicellular submaps of genus. So if you are on the two torus, you can take the one in the middle and take them as base of your matroid. It gives something nice, but I don't know if you can use it for anything. But
yes, if in the original bijection in genus 0, in the construction of the shuffle of two equals, the bijection is a pair of
yes,
trees. There was in the underlying the construction, in fact, appear a class of permutation,
yes,
which are exactly at the intersection of alternating permutation of 2n plus 1 element, counted by the tangent number, and the class of Baxter permutation. So the construction of the three people you mentioned was in fact a bijection with alternating Baxter permutation of 2n plus 1 element. So can you extend this to in a genus G? Is there a class?
in fact, I understand the bijection better if I just go from shuffle to pairs of trees, but
because the shuffle is a shuffle, we construct 4 perimeters. So in fact, we are constructing a complete binary tree with 2n plus 1 element and putting some labeling. So if you look at these trees with increasing labeling, this is in bijection with alternating permutation, counted by tangent number. And then in the case of we are working, the labeling, you don't need not the whole labeling appearing, only some label appear, and we are taking this sub-label, taking the reverse decreasing tree, and this was exactly the coding we need for the labeling, which gives the second tree.
yes.
So in the general case, it should be.
So for instance, I cannot interpret. I do not know how to interpret this big tree. The big tree in terms of maps, I don't know what it means. I can interpret the two trees that you obtain because these things are isomorphic, and I guess I can say that you are just constructing in the dark your bijection, your two trees without knowing how it works. But the bigger structure,
the biggest one, right?
I don't know how to interpret it. So maybe there is an interpretation, but I don't know it. So.
Okay, let's thank the speaker again.